EAA presents Jim Bede, designer and builder of new types of airplanes for general aviation. His sensational bullet-shaped Bede-5 has become one of the most publicized sport airplanes ever introduced. Here on videotape, he discusses topics common to all aircraft design.
This session we'll be talking about cooling drag. On an aircraft which is using a standard reciprocating type engine, it is quite necessary, of course, to provide adequate cooling for the engine itself. This happens to be an area that not a great deal of information is published about it. It is quite complicated and can vary greatly from one type of installation to another. But it's really quite important and quite critical to consider in the design of the aircraft. For example, here is a technical report done on the Bede Skyrocket 2. Now this is a composite aircraft, four-place, with a single engine tractor installation up front. And it's a rather well-designed aircraft, relatively clean, using a good laminar airfoil wing section. Just to give you a quick idea as to what we're talking about here and the magnitude of things, if you want to break down the drag of the aircraft, and this report actually did it, and it did it very scientifically, and therefore I feel it's quite accurate, you could take the fuselage, for example, and that accounts for 26.9% of the total drag coefficient. The horizontal tail is 11.4%. The vertical tail is 4.1%. Tail interference is only 0.3%. Wing fuselage interference is only 0.8%. The wing itself, the total wing drag, not including induced drag now, is 36.8. Now, cooling drag, after you look at all those things, cooling drag is 19.7% of the total drag. And at 200 miles an hour, this is accounting for 37 horsepower. So here is a relatively well-designed aircraft that just about 20% of the total drag of that airplane is cooling drag. So I think this is an area and a subject that really needs to be studied more, and the designer has to put a great deal of effort in analyzing it. Let's sort of review this thing a little bit. If we're talking about engine cooling, we really have four basic subject areas to think about. There aren't really a great deal of reference material available on it, but these are two that I think could help the general aviation designer the most. There is a reasonably nice report that is put out by Lycoming Avco Corporation. It's report number 674, and this deals primarily with the internal design of it. In other words, once the air comes in through the inlet, and how it has to go through the engine itself, and how you can determine the amount of air that should go through, the pressure drop that is required, and the amount of horsepower and drag that is produced by this particular installation. For different altitudes, this covers a supercharged engine, so you can study on designing cooling drag for high altitude conditions. There is also a NASA report, NACA report, that unfortunately is a wartime report, and they're a little bit hard to come by, but if that is something you can obtain, it's L491. And then there's a SAE paper done by Mississippi State University doing it. It's report number 770467. But whenever you're talking about cooling requirements for an airplane, you have these four major areas to be concerned with. One is cylinder cooling itself. The second is charged air, which is the amount of air you need to go into the carburetor. That's relatively straightforward. There's nothing too complicated about that. And the obvious thing you want to do there is be able to get as much ram recovery you can going directly up to the carburetor to the induction system so you can get maximum manifold pressure so you can get maximum horsepower. Then, of course, there's sometimes a requirement for oil cooler cooling, you've got to provide an adequate amount of air to go through the oil cooler itself. That in itself should be relatively straightforward, depending upon the engine and what the requirements are for the amount of air to go through the oil cooler. Then there's after cooler cooling, and this is if you have a supercharged engine, you want to be able to take that supercharged air and cool it before it goes into the induction manifold system. If it's not a supercharged engine, of course, you don't have to worry about after cooler at all. So in this case, we're going to really consider primarily cylinder cooling itself. What's required to cool the engine cylinders? This is the trickiest one of them all to deal with. The primary way is ram air. Some way you have an inlet and you ram the air through this inlet, goes through the cylinders, and then you dump it overboard through the cowling, cowl flaps or whatever might happen to be in there. There are two different areas that you have to really worry about. One is a tractor engine installation where the engine's up front, the propeller's mounted directly in front of the cowling, and we ram air in through the inlets openings. And the second is a pusher design, or really it could be even a water-cooled design. With a water-cooled engine, even if it's in a tractor position where it's up front like a P51, since you have water-cooled or liquid cooling system, you now have a radiator. And a radiator you can put any place you want on the airplane. Same thing with the pusher installation. If you have a pusher installation, you have a great deal of flexibility as to where the inlets come in. It depends, of course, on the design installation. In some cases, you really can't move the inlet opening in too many locations, but you do have some degree of flexibility to it. So the inlet itself is somewhat important as to where you put it relative to the rest of the airplane you go into it. Let's talk about that just a little bit further. Let's take a look at, say, a standard tractor installation. And this would be considered the firewall, and this would be the cowling itself with the spinner right in here. And we have the cylinders mounted in this region in here. We really don't have a great deal of options as to where we can start putting the air inlets on the thing. Obviously, we can get a little radical. We can put an air inlet down under in here, try and bring the air up through that region in there. We can try putting an inlet up on top in here and try to do something like that. But I think it becomes pretty obvious in both of those installations, you might get pretty good ram recovery because you're putting it right out in the free stream, but at the same time you're producing a great deal more of additional drag because you have to ferre that protrusion out, and also it's producing additional frontal area and everything else. So generally speaking, with an installation like this, you're pretty well stuck to dealing with some kind of zone right behind the spinner, right in the forward portion of the nacelle itself. And a lot of times, because of the engine itself, without any prop extension on it, you end up with a relatively blunt portion of the cowling right in front of the cylinders, right behind the propeller spinner itself. And so this becomes somewhat of the most natural place to try and put an air inlet in there. The thing you have to be concerned about here is the fact that the air is flowing around this cowling, and because of the bluntness of the cowling, it has to slow down and stop and go around the cowling itself. So that becomes an automatic stagnation point. That becomes an automatic spot where you do want to put your inlet in there. Somehow it seems to be common belief that you can control the amount of air that goes into the engine by how big you make the inlet opening. Well, that really isn't true. In practically every engine installation that you have around, the inlet itself is more than big enough. It will easily handle all of the volume of air that engine will need. What really controls it is how the air goes out. That's the area that can control how fast and how much air will actually go through the engine itself. So the inlet, in its design, the key thing we have to sort of be worrying about here is if we're stuck with a particular location, if we have to have it in one little spot in this particular region in here, you try to then have it in a zone that will be as close as you can to the natural stagnation point of the air flowing around the cowling, but yet at the same time in such a way that as the air flows around this inlet, it doesn't interfere anymore with the cowling or the rest of the airplane than possible. Let's take the same installation here and sort of look at a top view of the thing. If we're going to be dealing with these zones right in here, then we're going to have to try and see just which is the best way to try and get a particular inlet in there. If this happens to be sticking out and very blunt in here, then you've got a difficult situation to work with, but you're really stuck in putting your inlet right in that particular spot in here. what you can do is, depending upon the engine you have, you can take a look at the specifications on the engine, and it will tell you the number of cubic feet of air that has to go through the cylinders themselves and at what pressure drop. It takes very simple calculations to go ahead and determine at, say, climb speed configuration, which is probably going to be the most critical. You're not going very fast. You probably got the engine at maximum continuous power under these circumstances, so you need all the cooling air you can get, and you're not traveling at very high speeds. But you can very quickly determine the amount of area that's necessary to get that particular volume. It's good to look for a 20 or 30% increase in that volume, because if the calculations show that you need a half a square foot of opening in there, there is no way you can have just a half a square foot of opening and have all that air go right into that opening and then go through the cylinders. Obviously, there's a lot of spillage that will occur around there. In fact, it's sort of interesting, if you ever take an aircraft, run it up on the ground, go to good high power settings, and get one of these little signal smoke bombs, for example, and take the smoke and hold it in front of the propeller in here and see how you can possibly make that smoke go into that inlet. Now, when it's sitting on the ground, of course, with the cowl flaps open, you're not getting real good cooling, but you're getting some cooling. You can obviously take a look at the cylinder temperature, and you can see it's not just rising rapidly right through the red line. There is cooling going in. So therefore, there is air going into the inlet, there is air going through the fins, and there is air going overboard, even though you're standing still. But it's interesting. You can take the smoke bomb and you can hold it up in here, and smoke will go every place you can imagine, but you can hardly ever see any smoke going into that doggone inlet. So it's amazing how little amount of volume of air actually goes into it and how much is bypassing and going around. So that has a real critical thing to do. You have to just automatically assume that your inlet is going to be larger than you need. Make it 20, 30, maybe even 50% bigger than your raw calculation would be as to the cubic foot of air has to go through there. And realize that a lot of air is going to spill around it. Some will go into the inlet and some will come around. So the lip itself, the actual lip that you have for the opening, must be nice and smooth and round, anticipating that air will go into this region, not be able to make it, and turn around and come back out in this fashion like that. There was a case, for example, back in World War II up in Canada. They had the Cessna T-50s as a twin-engine trainer airplane up there, and during the training period in the wintertime, it was extremely cold. And in flying these airplanes, even though they were flying all day and they were doing touch and goes and so on, cylinder head temperature remained really low all the time. And it had no cowl flaps on the thing. So the maintenance people were really concerned, the operation people were concerned about the fact that these airplanes are flying with cylinder head temperatures as low as they were. So they wanted to do something to increase the temperature of the thing. Well, this was a radial installation. Let's draw the cylinders and the engine in here like this. And we had a cowling that came across something like this, and a hub, and we had the spinner, and well, no spinner in that thing, but the prop installation right in here. So somebody reasoned, if this is the baffles and everything else, and this is the cylinders right here, somebody reasoned that if they would take a board, plywood board, and cut it in a circular fashion and bolt it onto the engine, so that from the front view, you had the hub, and here was your cowling going around like this, that if you put this board in here, like this, that you'd block some of the air going into there. Well, that made sense, except for one thing. When they actually did this, what happened is the engine cooled even better. And they were dumbfounded, so they made the board even bigger, larger diameter, increased it out here, and the cooling still went down. Well, they decided, no, you're stopping now. They're running the test. Let's find out what's going on. So they kept making it bigger and bigger. And it got to the point to where this big circular board was within about 1.5 inches of the edge of the cowling here. And what they were able to determine as they did this thing was, without this board in here, what was happening was a lot of air was coming in. Some was going through the fins themselves, but a great deal was turning right around and coming out through the root section of the propeller itself. So a tremendous amount of air was circulating in here and actually coming out through the propeller and then eventually spilling out and around. By putting that first smaller size board in there, they literally blocked this air from coming out and increased the pressure and made more air go through the cylinders, and that increased the cooling. So when you take a look at a radial engine, you see this big opening in there, you can be doggone sure that a tremendous amount of the air in that total area is not going through those cylinders. In fact, it's turning around and coming back out in there. You can have the same problem with this thing. If your inlet is very large and particularly relatively close to the propeller spinner, there probably will be some air that's actually circulating and coming back out right at the root of the propeller hub itself, and portion of it, of course, is going through the fins. There was a study done by Mississippi State. This was done on an Aztec, and an Aztec had a standard cowling installation that looked pretty good. It looked like it had a reasonably nice low drag. It was sort of shaped like this, and it had somewhat of a rectangular type of inlet opening on the thing. But they found that this was not optimum, that there was losses there. There were spillage of air going around. It was producing drag. They eventually came up with a design that sort of didn't look too attractive, but from a front view, these were just like round openings here, almost like a 727 inlet opening or something like this, and he ferried it in very nice into the cowling, but they had this opening reasonably far away from the propeller center line, so that there was real high speed air, dynamic air coming off the propeller itself. They were able to get the inlet opening to be smallest. They were able to get the inlet drag down to about the lowest levels it could be. Sometimes this becomes rather critical too. These factors end up producing drag characteristics that are much worse than what we would anticipate. Here is a NASA report, TND 6800. This is all on a twin Comanche, and there was a great deal of study done on that. And here's a case of a plot of the cooling drag and drag coefficient along this line here versus angle of attack. And the interesting thing to note is here, this is 0 degrees angle of attack. At 8 degrees, the CD of it is really at its lowest level. At negative angles of attack, the, I'm sorry, I read that wrong. This is 0 right in here. It's still at 8 degrees, they had the lowest drag coefficient for that inlet. At 0 degrees, it was appreciably higher, 2 or 3 times higher. Somehow it went down actually when you went into negative angles of attack. But strangely enough, as you went from 8 degrees to 10 degrees, it really shot up. I mean, it multiplied itself 4 or 5 times. This is, of course, something a designer really would not like to have. You don't want to have this tremendous variation in drag coefficient due to cooling because of angle of attack. In this particular case, it has to be carefully looked at as to whether this was due to the inlet or whether it was due to the exit area where the air was being discharged, or maybe the combination of both. It could not have really much to do with the baffling inside the engine, because that is not a function of angle of attack. While we're talking about the inlet opening itself, I'll give you another area that presented a problem for one of the companies with a twin-engine airplane. They had a design where they had cowl flaps sitting here on the bottom that could open and close. And they had a particular airplane already in flight test and going through all of the development work with the thing. And one thing they noticed is that in cruising condition, they had adequate cooling with the cowl flaps closed, everything was fine. But when they opened the cowl flaps at cruise speeds, they actually increased their cruising speed at exactly the same power setting. So it meant that they actually reduced the drag of the airplane somehow by opening up the cowl flaps. Well, that was violating all the standard rules, because by opening the cowl flap meant that you had to be bringing more air through the cylinders themselves, which means as you bring more air, you're creating that drag, and therefore that's got to be an increase in drag. Well, that was true. In fact, they found out that the cylinder head temperatures went down, but the airplane still increased in speed about 6 miles an hour. Now, this was an appreciable amount. And they tried to analyze how is this possible to be done so that when we have the cowl flap closed and a reduction of the drag of this cowl flap sticking out into the airstream and a reduction of air going through the cylinders, we actually still have a total drag reduction. Well, what they found by analyzing is that this inlet here was sticking up so high and it was so sharp that by closing the cowl flap and restricting the amount of air going through the inlet, that a tremendous amount of spillage air came up over the top. This spillage air over the top caused significant separation on the cowling and caused an increase in drag. By opening the cowl flaps and allowing more air to go through the cylinders, the spillage air reduced itself, the air reattached to the cowling, and therefore the drag reduction of this area was so great that it totally counteracted the increased drag going through the cylinders, and the net result, a 6 mile an hour increase in speed. So a proper design of the inlets is really quite important. It's not necessarily the most important thing you have to worry about in cooling design, but it is important. It is something to really think about and work on. Initially in your design, if you don't have the access to wind tunnel and so on, all you can do is use good judgment, good aerodynamic practices and thoughts on the thing. But once you get into flight tests, then you can start putting tufts around here. You can start visualizing what the airflow condition is. You need a chase plane sometimes to be able to photograph that. With the new video cameras you have right now, you can get some real good movie results of the thing. See what your tufts are doing. Be prepared to modify the inlets of the cowling itself to get you better flow conditions. But if you do, you can really start attacking that 19.7% drag of the total airplane. If you can reduce that 10 or 15% or maybe cut it even in half, which is entirely possible, 37 horsepower, it's an awful lot. When you start doing something like that to the airplane, that's just as important as trying to reduce the size of the tail or the interference drag or covers around your wheel wells or something like that where you're attacking. This is an area that really a lot of work and a lot of effort should always be put to it. Let's take a look a little bit more at the pusher designs and or water-cooled engine installations. Now let's take this pusher airplane. This is your propeller installation, and let's, for the sake of discussion, assume you have a wing down in here. And let's assume this general region is where your engine itself is going to be. You can bring air in from a zone right here. And the thing, you can bring air from up on top. You can bring air from underneath on the bottom. There are several regions now where you can start to bring inlet air into there. What you want to, of course, do is two things. One, you want to bring a inlet itself so that you can get a reasonable amount of ram recovery of the airflow around the aircraft itself. But you also want to do it in such a spot that you have a relatively low drag input of the rest of the aircraft itself. This region right in here on top of your wing or right near your fillets in this zone right in here, this is a very, very sensitive area. This air flowing over here has a lot of reasons why it wants to separate from the surface, it wants to become turbulent, it wants to produce drag. Doing anything at all in this zone here, right where the wing intersects with the fuselage, whether this is low wing, mid wing, or high wing, any one of these cases, the condition is the same. It's sensitive. It's not necessarily the best place to try and put an inlet opening because you will not only have maybe poor dynamic recovery, but you have a good chance of having flow separation, and if flow separation going on back will cause a very large increase in drag on the airplane. This region up in here, putting something up in here, is not really all that bad, but under high angles of attack, under climb conditions, you're not really getting the best dynamic pressure up on top, and therefore it could be somewhat sensitive. You could have a flow configuration coming over the fuselage, or depending upon how your windshield looked in here, in such a manner that you might actually start to reduce the dynamic pressure, the ramming air into this inlet, and therefore under climb conditions, which is probably your most critical condition at all, you really won't have good recovery. And so that zone there has a lot to be thought about and desired as to what the problem is. Second thing is high angle attack. Any protrusion you have sticking up in above the fuselage in there also has the capabilities of having flow separation off of it, and therefore it might be more difficult. On the other hand, you may have a design installation such that let's just look at something like this, where your engine is right back in here, real high. You have a blunt arrangement, and you have your spinner and your prop right in here. And for other reasons down in here, this really becomes the only zone to do it in. Okay, fine. This is something you have to do. And if you're going to do it, it's probably good to have your opening far enough forward so that you can get a nice, good, smooth fairing in here. Once you've got that inlet, remember, not all the air is going to go through that opening. A lot of the air is going to go around it. It's going to spill over it. You want to be able to keep that air attached to the surface and flowing in, particularly since you have a propeller back in here. If you have flow separation going into that prop, you're going to not only have the drag of that flow separation, but your propeller itself is not going to operate too well inside that turbulence air. It's going to make a lot of noise for one thing, but from a performance standpoint too, it will have a definite loss of efficiency of your propeller itself. So it's a double factor here to keep that flow attached, have it nicely flowing into the fuselage. On the other hand, if we go back to this, and if you have the option, this zone underneath here, from this portion of the wing, about 1/3 back from the wing aft, that whole region underneath there is an extremely good region to try to have recovery air for cooling. The P-51 installation, of course, is the perfect example of that. They had their cowling underneath in here like this, and in fact, that was one of the very major factors of why the P-51 had some of the performance gains that it did have. This region in here is right below the wing at high angle of attack, low speeds. The wing is doing a significant amount of lift. It's a pretty good CL. There is a great deal of static pressure increase in here. It's also a region where the flow coming into that inlet is unobstructed. You're going to get maximum ram recovery. It's in an area that's not sensitive to flow separation and so on. And even in the case of the P-51, they have a way back and then they have the cowl flap doorway in the back region in here, that turned out to be an extremely good insulation. In fact, it got perfected so well that by the final designs of the P-51, the inlet air coming in, the amount that spilled around, and the amount of air that went through there and went through the radiator had to be slowed down. There was a momentum loss there, therefore there's a drag loss there. But as it went through the radiator, it actually got warm and became a tiny little jet engine. And as you could close the cowl flaps and let that warm air, relatively warm air, go roaring out the back, it actually increased in velocity. So there was a slight jet thrust action out of that installation. And the net result is that NASA claims that by a properly designed system that they had here at high speeds, they had essentially zero drag due to that installation in there. And that would be, of course, the optimum to go with. So on a pusher design or a water-cooled design, you've got a variety of places to look for as to where you want to put your inlet. And the ideal region is below the wing and just slightly aft of the bottom of the wing. If it's a high wing installation, then the influence of the wing of this pressure region is not as critical anymore. Still down underneath might be good, or conceivably along the side of the fuselage there. We've been talking about the inlets, the ram air inlets, and the basic location of the inlets based on the tractor or the pusher. We've talked a little bit about the size. If you don't want to go through a lot of calculations, you can take a look at other aircraft engine installations using your type of engine and get a basic idea of the size of it. But point I really want to get across is that in practically every case, your openings will be more than big enough on it. The shape of it, the shape of the opening itself, of course, there's some aesthetics involved, some good aerodynamics involved as to the actual frontal area shape, but the critical thing here is the lips around the opening. Make sure those lips are nice and smooth and round so that any air that goes into the inlet and doesn't want to go through the cylinders themselves can come back out, flow around, and still stay attached to the cowling. If the inlets are very, very close to the top of the cowling and the top of the cowling is very flat across there, you can visualize, obviously, that it's going to be quite difficult for the air to go into the openings, turn around, come back out the inlets, and then back out over the cowling without separating. If it's down lower into the center of the cowling itself, where there's a nice curved portion above, around the sides, and underneath, then, of course, you can visualize it'll do it. We have the old NACA type inlet, the very flush, streamlined inlets. This is a nice inlet for several reasons. One, it has very, very little aerodynamic drag to it. Two, because of the vortex of the air flowing into the inlet itself, and I'm sure all of you are familiar with the one I'm talking about, shaped like this, the air flows around and spins into this opening here on a 7-degree ramp that it has, and very little ice or particles, rain particles, will go into the opening. That's good. What happens is, however, is you cannot get complete ram recovery in this. On a perfect installation, you might get 97, 98% ram recovery. In other installations, other variations of this thing, you might have much lower than that. So you don't want to use a NACA type inlet unless, of course, you're using it in a particular installation where you absolutely want to keep the drag level down to the lowest as far as the external drag surface goes, and you're willing to suffer with some losses of ram recovery on it. So that type of inlet has to be used at the proper time, at the proper place. There's some things for cabin installations, cabin heat or something like this, where you don't need 100% ram recovery. That's fine. Let's go on to the next area here, and this is the baffles themselves inside. Fundamentally, we have two types of baffling system. We can have a baffling system where, well, let me redraw this thing, where you have a downdraft or you have an updraft. And let's talk about the standard cowling configuration. And we have the cylinders in here. You can either have the air come down through the cylinders, or you can have the air going up through the cylinders. Frankly, either method is about the same. It sometimes depends a little bit more on the engine installation itself. And today with the 4-cylinder or 6-cylinder horizontally opposed, the most common system is a downdraft system where the air comes in through this opening here, flows down through the cylinders themselves. Normally speaking, the exhaust pipes are down underneath in here too, so that the warm air coming through the cylinders is not preheated by the exhaust pipes is what you would have if the air was going the other way. If you have an updraft, some of the cooling air coming up through, before it gets into the fins, will have to go around the exhaust pipes themselves. They're very, very hot. They'll transfer some heat. The air will get warmed up. You might have a little loss of efficiency there, but that's not necessarily a critical thing. And there isn't a great deal of data showing that there's a significant difference between updraft and downdraft. A lot will depend on your cowling arrangement and so on. Normally, it's downdraft, and that's the type of situation that most aircraft end up with, and that's the one you can sort of take a look at. There isn't too much you can do in here, unless, of course, your baffling is very poor. If you don't have it close up around the cylinders, if you have gaps or openings in other spots, you're going to now have ram air that's coming in, cooling air that's coming in, that never goes through the cylinders. It goes around it. Well, that's drag. That's internal drag. It did not help cool the engine. In fact, probably hurt in cooling the engine because it had a loss of pressure drop between the two areas, the cooling air and the plenum chamber below it. And therefore, you have a total increase of air flowing through the cowling, and that's an increase in drag. So try to get the thing reasonably well sealed so you don't have those particular losses on there. But what's done inside the engine cowling can best be analyzed by getting a hold of that Lycoming report, for example, and studying some of that. But there isn't a whole lot you can do there. The engine itself is the way it's designed. It requires so much airflow to go through the fins, and all you can do is seal it up best you possibly can. Next region that we have to consider is the exit itself. Where does all this warm air come out of the cowling? That is probably the most critical thing that we have to worry about, because the exit controls several things. One, it controls literally the volume of air that's going to flow through the cylinders themselves. If we have anywhere near an adequate opening in the front, by controlling how much the opening is in the exit portion of it and where its location is, will have a great deal to do with how much volume comes through. You can throttle it down or you can increase it, particularly by cowl flaps. The pressure differential, that will have a great deal to do by the exit area itself. When you're flying through the air, the maximum you can do is take this dynamic air flowing at you at 100 miles an hour, 120 miles an hour, and slow it down to 0. Once you stop it, that's all the pressure recovery you can get. Now, when that goes into the one chamber, if this chamber that it flows into, the plenum chamber that it flows into, if that is choked off so much, its pressure will be the same as both sides, and therefore you'll have no flow through it. As you open this up, you will gradually be reducing the pressure on the warm side of the engine itself, and that will cause the pressure differential. So the exit air, the cowl flaps, they have almost direct control of what the pressure differential is between the top of the cylinders and the bottom of the cylinders. Cowl flaps, of course, are the best way of doing it. This is little devices you can put on the bottom in here. From a end view, you might say on the thing, this might be the bottom of the fuselage. Maybe you have an opening already right in here to let the air come through, and you can have your bottom of your fuselage like that. That's a real good installation. And then when you have the cowl flap and you lower it, you've had this much increase, or this total amount of area, this much of an increase of exit area, and now the volume of air and the pressure differential can be at its maximum. This is a condition you might want to do while you're climbing. You don't have a great deal of forward speed, and you need all the cooling you get. But once you get up in the cruising speed, you're going quite fast, you got real good dynamic pressure, and you don't really need that much cooling air. Now you can close the cowl flaps, restrict the area, and have adequate cooling, but no more cooling than you really have to have, and therefore no more drag than you need to have. The two areas when we're dealing with this thing that we haven't discussed yet, one is an exhaust pump using the exhaust itself as a thrust augmenter. The engine itself, say this goes into some sort of a manifold, the exhaust itself is high energy air being pumped out. You can put that into a form of a venturi. You can make a little venturi here, And this becomes a jet pump, as it's called, or a thrust augmenter, whatever way you want to look at it. It becomes a very interesting way of reducing the power required for cooling of the engine. The difficulties of the exhaust pump, or the jet pump, is the fact that, number one, you cannot control the exit air very well. You cannot put cowl flaps on the exit area of the pump itself, because as you start to restrict that, or restrict the cooling air, you're also starting to increase the back pressure of the exhaust pipe itself, and that's detrimental. Also, you're dealing with somewhat contaminated air. This is not just plain cooling air coming through the fins now. This has got the exhaust itself with all of the fumes involved with it. And the second thing is that you generally have to have a fairly long augmenting tube there. When you have your Venturion here, you have to have a relatively long pump to get the proper jet pumping action to it. And then third is it is quite noisy. This is no way of actually reducing noise. In fact, it almost becomes a megaphone and increases the noise. We used to have the Convair 240 and 340s and so on had jet pumps. They were some of the early ones to use. And then on general aviation airplanes, we had the Twin Bonanza, and we had the Aero Commanders and so on. That system has been pretty well eliminated. It's there. It does produce a certain degree of efficiency of reducing the power required for cooling of the airplane, but the disadvantages sometimes outweigh it, and it isn't really worth it. The other thing that we have to really consider in any of these installations is the exact location of where this cowling air goes out, where this cooling air goes out, where you have your cowl flaps. The general common one is down underneath the cowling here and the bottom of the fuselage. There's some really advantage of that, because you generally will have any oil leakage or any kind of fumes or anything like that will then flow out through the cooling air, go out through the belly of the airplane, and just from an aesthetic standpoint, you don't look like you have a very oiled, greasy airplane installation. The top of the cowling in this region here, aerodynamically, there's some really nice regions for that. Particularly at high angles of attack, this becomes a region of lower pressure, and this is an area where it'd be very nice to let this hot air come out into there. But of course, that almost restricts it to an updraft installation, or it requires you to come back into this region in here. Aesthetically, it might have some problems with it, and there may be some other difficulties. Along the side of the cowling is another potential area, but there's really no big advantage there unless it's just more from a manufacturing aid or anything else. When NASA did some studies way back in cowlings with the old radial cowlings that they had, and put the spinner in here, for example, here's the engine installation. If this is where the air went in, they found the very best place is to have the exit air right in this region in here. They would have to have a double cowling in here, and the air would go through the cylinders and through the fins, turn all the way around, come back in here, and then out in this region like that. By having the air go in this region and come out very close to it and add it to the slipstream again, very close to where it went in, turned out to be the lowest drag region. But the reduction of drag of this exit area isn't really worth all the complications and all the difficulties that it puts in it. I've only seen one airplane ever designed and built and flown that way, and this is the old Curtiss 047 observation airplane. Had a big radial engine that had some openings right around the periphery of the cowling inlet there. But even though this is maybe theoretically the best, it has a lot of practical limitations that isn't really worth talking about. We've been talking all this time about ram air cooling. There's another area that we really got to consider, and that's blower cooling. What if we did not worry about ramming the air through all these fins and cylinders and areas triangle? What if we actually took a blower? We could either use an axial fan blower, we could use a squirrel cage blower, or essentially a centrifugal type pump, or we can even use an electrical blower. We could have a blower of some sort driven by an electric motor. There's a lot of merit to this. There was a lot of work done at the end of World War II. The Germans did it, we did it, where we'd actually have a cowling installation. Let's go back to something like this in here. And fins, propeller blades were actually installed right to the hub. And instead of just ramming air, we had a controlled axial fan that pumped the air into it. Now when you start thinking, for example, on the Belanca, where 37 horsepower is being used to cool that thing, you can imagine that you can make a mechanical pump, axial fan or squirrel cage, even with its losses and inefficiencies, to produce all the cooling air you want to have to cool that engine without having to worry about aerodynamic drag. Most of the designs that I've ever seen using some form of a blower, a squirrel cage blower, an axial fan, or something like that to cool it. In practically every installation I've ever seen, there is definitely a drag reduction, a horsepower requirement reduction. So going to a mechanical driven system for cooling, I think is an area that has a lot to be yet worked on, and I think it can actually turn out to be a real good system with it. It's a little bit like saying you have a generator on your engine right now to produce electrical power. Old days we used to hang one out in the wind and ran it with a propeller. Well, we soon found out that ramming air through that propeller to give us electrical power was not nearly as efficient as having it attached directly to the engine itself. Now, it takes power off the engine, there's no question about it, but it's a far more efficient way. And the beauty of it is by having an actual blower to do your cooling, you can now have it proportional to engine speed, and maybe therefore exactly the requirements. As you slow the engine down, you sure as heck cannot be going to maximum horsepower, therefore you don't need maximum cooling. So when you're at maximum horsepower, maximum RPM, that's when your blower is going to do the best job, not a function of forward speed. Now, you still could use a blower and then use good aerodynamics as to where the air comes into the blower and where the air goes overboard. So therefore, once you're moving through the air at 200, 250 miles an hour, you don't necessarily have to use the ram recovery, but you can use it in conjunction with your axial fan to reduce the power requirement that the fan itself might do. So I think this is a region that even with general aviation airplanes and small light airplanes, we ought to take a real good look at the possibility of using blowers on there. An axial fan, when you get down real small in diameter, has to turn pretty fast, so you have to maybe speed it up fast than the engine goes. But a squirrel cage blower, it will produce all the pressure differential we need and all the volume we need, turning at about the same RPMs, 2,000, 2,500, maybe 3,000 RPMs at the most. And so I think some clever work can be done there. Of course, helicopters for years now have been using engine installations, and they put fans on there. Again, if you study it real carefully, you're going to find out that the power required by the blower to run those fans is always less horsepower than you've ever determined, calculated by using a ram air method. The ram air method's simple, there's no extra parts, it doesn't break on you. Once the airplane's flying, you're getting cooling air. But on the other hand, if you're looking for best performance and maximum performance, maybe that's the way to go. We've studied pretty well all of the factors that are involved in engine cooling. This is a subject that unfortunately not a lot of data has been printed and published about. It's there, it can be found. It's somewhat sketchy and somewhat fragmented in the fact that a lot of times they'll talk about specific things that go with it. It's just like when you're designing an airplane and building one, you look to see how the top looks and you try to make it real streamlined, and somehow you like to hang all the pipes and antennas and all the drag producing things down under the belly of the airplane. And you think because you don't see it, it doesn't cause drag. Well, that isn't true. Of course, on automobiles, they make the top real streamlined and the belly of the car is just piled with a lot of junk and a lot of obstructions and therefore a lot of drag. The truth is, it does produce drag when you're dealing with the belly of the airplane. The truth is, a cowling engine does require proper design to get the least amount of drag through it. Just because you can't see it, just because it doesn't look like it's got a lot of drag, doesn't mean it is not slowing that airplane down. And of course, the best thing to do is use your head, use the best technology, the best knowledge we have in optimizing your cooling, and that can become a significant part, up to 20% or even more, of your total power requirements at cruising speed now. Why not try to do something to whittle that down? We've done a lot of work in making good airfoils. We try to get our tail as small as we can. We try to get good interference fit of our control surfaces to our fuselage. Let's now work on cooling drag, and I think there's a lot of benefits that can be gained from that.